All right, good afternoon. Thank you, that one person that replied. Oh, now you're going to leave, guys. I haven't even started yet. Yeah. So today we're going to talk about the transport architecture in Exchange 2013. How many of you know what the transport architecture is in 2013 today? One person here. So I can sit down. Come on. How many think the architecture is improved? Okay, a few hands. How many think the reverse? That's the scary part. Okay, nobody does. Everybody else is just curious. All right, good. So, simple agenda today. I want to go over what the transport components are in Exchange 2013. We'll discuss a little bit more of the architecture that is in Exchange 2013 because it directly applies to why we made the decisions around the specific components we now have in the product. We'll talk about some of the improvements that have occurred as a result, and then I'm going to go through a series of mail routing scenarios. No demos today, since my demos yesterday kind of did that best thing. So we're going to do scenarios instead. And then we're going to end with built-in redundancy. Talk about our resiliency features. So unlike the past two releases, Exchange 2013 now has three major components for transport. We looked at transport and decided we needed to break it along three key areas. First one was that we had a goal where the client access server would become a proxy. So we decided that we should actually ship a stateless transport service on the client access server role that could be used for doing proxy-related functionality for messages coming into the organization, whether it be a SharePoint application or a POP or IMAP or internet-based mail, as well as a means for us to get that mail outside of the organization boundary. So that's the front-end transport service. I may refer to it as FET several times during this session, so if you hear me use that term, that's what it means, front-end transport. And then we have the transport service. The transport service is what we used to refer to in 2007 and 2010 as the hub transport server role. This is the stateful SMTP engine that we have within Exchange 2013. By stateful, I mean that there's an actual queue. And then finally, the last component, which is the transport service and the mailbox transport service, are both located on the mailbox server role. And the last component is the mailbox transport service. This is very similar to the front-end transport service in that it is stateless as well. It has no queue. But we'll talk about specifically what these three services do within the product. Transport responsibilities, however, have remained unchanged. We are still the core routing engine for getting routing mail within the organization, as well as making the decisions of how we route mail outside the organization. We also are still primary for policy enforcement, for our transport rules, and for data leakage protection, and so forth. It's also where we do all of our malware scanning. So none of that functionality has changed. It's still there and still exists the way we've always done it in the past two releases. You can still extend transport with transport agents and routing agents and act on things at certain parts within the transport pipeline. So the architecture. The architecture is as simplified in Exchange 2013. We removed a bunch of core server roles and we collapsed them into two primary server roles. We have the client access server role, which is primarily responsible for authenticating all client traffic and making an intelligent decision of how to get that traffic to the mailbox server hosting the active database copy. And then we have the mailbox server role. And the mailbox server role hosts all the core components: transport, unified messaging, client access protocols, and the like. We form a bunch of CAS together into collectively an array, which is just nothing more than a load balance pool of CAS members that can then be used for connectivity for your end users. And then we have the mailbox servers, which can be joined into a database availability group to get you that high availability and resiliency functionality that you need for your messaging environment. There's this principle that I talk about a lot. Every server is an island. This is the key principle that drove all the decisions we made around the product in the development of Exchange 2013. So let's take a look at what I mean by every server is an island. I have two servers, server 1 and server 2. We can pretty much break these servers down into three key dimensions. We have the protocols at the top. Within our second layer is our business logic layer, which would house our extensible storage objects, XSO, content transformation services for things like the indexing service and the like, an exchange system object library. And then we have the storage layer, extensible storage engine, file system, the database file, the content index file, and the like. Very similar to the OSI model. We have at the top, we have the application layer, and down at the bottom, we have the physical layer, right? The problem with the past two releases is that we would allow communication to occur between any one of these layers to another server. So if I have server 1 that's operating, I don't know, Exchange 2010 Service Pack 1, and I have server 2 that's operating Exchange 2010 Service Pack 2. This is what could happen. I have a transport service that could communicate directly with the store on server 2, invoking store driver for message delivery. That would use an RPC to communicate. Where does this become a problem? Well, what happens if on server 2 we decided to deprecate one of the commands that server 1 is using? Server 2 would then no longer understand how to ingest that message that was just sent to it, and that message delivery would fail. The converse is also true. Server 2, which is a higher version, could attempt to submit a message to the transport stack on server 1. If server 2 only knows how to use these new protocols, and server 1 doesn't know how to understand these new APIs, we're going to have a crash. This is why we had specific version boundaries in Exchange 2007 and Exchange 2010. This is also why between those two major versions we enforced a routing version boundary that required a 2007 hub transport server to be only able to deliver to a 2010 hub transport server, and then the 2010 transport server would deliver to the 2010 stores. And the reverse was true for 2007 mailbox delivery. This is bad. This gives us our version dependencies. So in 2013, we removed that. We force all communication to go through the application layer, through the transport protocol or MRS proxy or the Exchange Web Services, if we need to do some sort of communication for data on another server. So from a transport perspective, if I need to deliver a message from server 1 to server 2, I'm going to do that via SMTP. I'm not going to use RPC anymore. So it's an SMTP path. SMTP is fairly well known. You've got hello, mail from, receipt to, data. Right? That's the simplistic view of transport. It's simple, remember? That's what the S stands for. So we block all these inter-level communication paths. So a transport service on server 1 in Exchange 2013 cannot invoke delivery to store via the store driver on server 2. It has to do that by going through the SMTP stack on server 2. Which means that anytime I need to do a message delivery, it's always going to be local to the store instance where that user is housed. That way we get rid of the version dependencies, because now the transport interface that's actually going to do the MIME to TNF conversion is always going to be local to that database, which means we never have to worry about any sort of wacky conversion issues. Whatever that version the store is, that's the version the transport instance is running, right? So that's our every server is an island principle. So the key to enlightenment, which, as I joke for those who know the answer is 42 for most people. But in our case, it's that for any given connectivity, to service a given user request, that's always going to be serviced by the protocol instance that is local to the active database copy. A protocol instance on server 2 is not going to process a request for a mailbox whose database is active on server 1. It will never happen in Exchange 2013. It will always be server 1, or server 2 in my example. Server 2 would be processing that request because the database is local to server 2. Does that make sense? Excellent. You can go to sleep now. So the transport components. The benefits of the front-end transport service. It really, you can boil it down to being that this front-end transport service solely provides you a means to have a unified namespace for transport, which can then be used for SharePoint applications. It could be used for internal SMTP applications. It could be used for your POP or IMAP clients. Now, why does that provide a benefit? Because you're already putting CAS in a load balance pool, which means now all you have to do is create a rule for TCP 25 or TCP 587, depending on how the client's configured, and have that get load balanced across all the members in that load balanced array. You don't have to do any complicated, crazy configuration like you had to do in 2007 or 2010, because back in those two releases, we were very specific in our guidance in saying that the receive connector could not be behind a load balancer because we're already doing load balancing within the application stack, and you'd mess us all up for transport-to-transport delivery. So you'd have to go create specific silos for transport to get a load-balanced transport service in Exchange 2007 or 2010. We're now providing it out of the box. You're already going to have a load balancer, so now you just need to add the TCP 25 and the TCP 587 rule, and you get a load-balanced solution for all transport delivery. That can be used for authenticated deliveries, and it can be used for unauthenticated deliveries. This could be your first hop, in quotes, from the internet, for example, if you so wanted it to be. So how does it work? As I mentioned, it's extremely simplified. We have two key components within the front-end transport service. We have the SMTP receive, and we have the SMTP send. Notice there's no categorizer. There's no delivery queues. There's no queues at all. It's stateless. It's simply doing a layer 7 proxy. It establishes the connection from the source, and it proxies that data to the target. The inbound for external-based connections is going to be either TCP 25 or TCP 587. If we are delivering mail from the mailbox server, so the mailbox server is attempting to deliver mail out to outside the organization, you have to configure that. Out of the box, it doesn't occur. You have to set on your send connector the front-end proxy enabled bit for that particular Active Directory site. And once that bit is set, then all mailbox servers within that Active Directory site that are scoped to that send connector will then use the client access servers within that local Active Directory site for message delivery, going out to the internet or to wherever the front-end transport service is configured to deliver mail. That will use TCP 717 as its TCP port for mailbox to client access communication. So because we have no categorizer, there's no bifurcation here. So if a message comes in destined to a delivery group, not to a delivery group, a distribution group, there's no expansion. It simply will route that message to the best choice mailbox server, which typically, in most cases, is a mailbox server that is local to the client access server for delivery. The mailbox server, the transport service, will then be responsible for doing the categorization, which will bifurcate the message and generate the copies for delivery along the least cost route. So the transport service. As I mentioned, it was what we used to refer to as hub transport. So you still may see in 2013 guidance the concept of a hub transport, but that has kind of gone away. We just refer to it now as the transport service. It is a stateful engine, so it does have a queue. The mail.queue exists on the mailbox server role. I don't know if Jeff talked about in his sizing session, but where we recommend placement of the mail.queue is on the system drive for most scenarios. So it's no longer necessary to dedicate a dedicated set of spindles just for the transport queue unless you have a capacity-constrained system drive. It still is responsible for performing all those routing decisions that we've done in 2007 and 2010. It still does all the policy enforcement that we need to ensure that, to determine whether we're going to route that message or block that message from being delivered. It still handles message delivery through connectors. So if you have a specialized connector, that's where this would occur. It still allows for extensibility. So those custom transport agents that you might deploy is where that would be installed on the mailbox server role. Journaling, transport journaling agent, still executes within the transport service for those that are doing journaling. How many of you do journaling? Out of all those with your hands up, how many of you are doing journaling for the message envelope specifically? Just a few. Okay. The rest of you are just journaling to archive then, I guess. You know, we have a solution for archive. But that's not this session. The other thing that we do with within the transport service is ensure that we redundantly persist the message so that in the event of failure, we can recover that and not lose that particular message. And we'll talk in detail about this concept of shadow servers and how we do redundancy, what we refer to as guaranteed redundancy in Exchange 2013. So, transport service looks very similar to what you used to see in the Exchange 2007 and Exchange 2010 guidance, or any of the architectural diagrams. There is one key component that is missing from this diagram: store driver. There is no store driver in the transport service within Exchange 2013. The transport service is solely doing SMTP. It's not doing any content conversion, no MIME to TNF. It is just getting the message to the best location. The mailbox transport service, which we'll talk about, handles that in particular. But as you can see, we are listening on one of two ports, TCP25 or TCP2525. The difference is whether you're doing multi-role. If you have client access and the mailbox server role co-located, client access is listening on TCP25 on its receive connector. So the mailbox server role's transport service is listening on TCP2525. Otherwise, if it's a dedicated mailbox server role, it's also listening on TCP25. It doesn't have any conflictions there. We still do content inspection here. So this is where all the malware will be evaluating those messages to determine if they are healthy or unhealthy or suspect, depending on how you want to look at it. Once a message comes in through the SMTP receive, the routing agents are enacted. The message is placed into a submission queue. That message is then categorized. We'll bifurcate that message if need be and place the message or messages into corresponding delivery queues. Those messages will then be submitted via the SMTP send and sent on their merry way to whatever that destination is. That destination could be a client access server role. So we are routing through CAS for the ultimate endpoint destination if that message is leaving the organization. That message could be being sent to another transport service within the organization. Or it could be sent to a third-party SMTP stack if you're having mail go somewhere else into the organization or outside the organization. All this is still wrapped within the same executable that we shipped in the last two releases, the edge transport.executable. So nothing here has really changed other than the removal of store driver. That's where the mailbox transport service comes into play. You can think of the mailbox transport service as conjoined with store. This is where we enact that every server is an island principle. So a message will come in to the transport service. The transport service is going to do that bifurcation. It's going to do that discovery. It's going to do a lookup. Which database does this recipient reside in? It will then route that message via SMTP to the mailbox transport service. The mailbox transport service is always going to be the local protocol instance that is local to that active database copy. It will then do the MIME to TNF conversion and deliver that message via RPC to the store. That is local to it. So it's all local RPC. This is what it looks like. It's very similar to the front-end transport service. There's an SMTP receive component and there's an SMTP send component. The mailbox transport service is broken up into two specific processes. There's MS Exchange delivery and there's MS Exchange submission. MS Exchange delivery, as its name kind of implies, is used for delivering messages into the store. So a message will come in via TCP 475 from the transport service. It will go in through the SMTP receive agent. It will be placed into delivery. We'll do our content conversion. And the deliver agent will deliver that message to the local database using RPC. Now, you will notice that the MS Exchange delivery process actually has an SMTP send component. This has to do with side effect messages. This is when we deliver a message and we need to generate a delivery receipt or a read receipt or an NDR and so forth. Anything that's generated as a result of that message delivery is what we refer to as a side effect message. In effect, journaling reports are side effect messages. They occur at the level above in the transport service. But this is what we would do. So we'll generate that message and submit that back to transport for delivery back to the recipient for that side effect message. Likewise, if we have a message that we are submitting via one of our clients, Outlook, OA, ActiveSync, whatever, that's going to be placed into the submission. The store is going to populate that via the MS Exchange submission service. We'll do our conversion from TNF to MIME. It'll get picked up by the submission service. Our mailbox assistants will execute if need be. Our submit agents will execute, and that message will then be handed off to a transport service for delivery into the organization or outside the organization, depending on the ultimate recipient endpoint. There is no extensibility within either of these two processes. So again, all the extensibility is done at the transport service. There's no other means to mess with that message once it gets to this layer. Any questions on these three processes at this point? Excellent. So routing enhancements. One of the key changes we made in routing in Exchange 2013 is we've introduced this concept of a delivery group. There are several different types of delivery groups. In Exchange 2013, we now have a concept of the DAG as a delivery group. And we refer to it as a routable DAG. This is an Exchange 2013 DAG specifically. So all the mailbox servers within that DAG naturally are Exchange 2013. We will use delivery groups for routing to determine, and they are used for along the least cost route to determine how we get the message. We prefer routing to the final delivery group if at all possible along that least cost route. So think of it in this way. I have a message. I need to deliver it. That message, when I do the recipient lookup, I determine that that recipient is within a database that is part of an Exchange 2013 DAG. I look up the least cost route. I say, okay, I can get this message from AD Site 1 to AD Site 2. Instead of just choosing a random transport server in AD Site 2, which is what we did in 2007 and 2010, I say, this guy's in a DAG. How about I just deliver this to a transport service on a mailbox server that is part of that DAG? And then we get the message to deliver to the store. So we'll prefer the DAG over any other transport service running in that Active Directory site in that particular case. We also have other delivery groups. We have the mailbox delivery group. Mailbox delivery group is used in a native Exchange 2013 environment for any scenario in which you don't actually have a DAG. So just a standalone mailbox server. It's also used for 2007 and 2010 for mailboxes, for delivery to a mailbox that is versioned for 2007 or 2010. So that's the final destination is one of those mailbox servers. We also support connector source servers, so when you define, like on a send connector, that you're targeting a specific mailbox server or a set of mailbox servers, that's a delivery group that will want to route to one of those servers on that defined connector. We have the concept of an AD site. The AD site here really is used for hub sites and edge subscription sites. A hub site is one where you specify that you want all mail to route through that particular Active Directory site, and mail must queue along the least cost route at that particular Active Directory site. It gets you back to like the Exchange 5.5 and 2003 type of routing topologies. And then edge subscriptions are when you deploy an Exchange 2007 or an Exchange 2010 edge transport server. It's scoped to an Active Directory site. All the hub transport servers at the time that you created the subscription can be used for message submission to the edge transport server role. So that's what an edge subscription is. And then finally, the last one is a server list for a delivery group. This is when you specify a server on distribution group expansion. How many people do that? It's a single point of failure. I don't recommend it. That's just my view, though. Once we get the message to the final delivery group, the transport service will then deliver that message via the mailbox transport service to the database, like we've already talked about. The routing logic predominantly hasn't changed, though. We still use least cost routing. We still determine at time of delivery what the least cost route is by calculating the least number of hops and the cost of each one of those hops. In the event that we have two or more routes that have the same cost, we look at the route that has the lowest number of hops. In the event that two or more routes have the lowest cost and the lowest number of hops, meaning that they both are exactly the same, we choose the one that is lower on the alphanumeric scale. So that part hasn't really changed in terms of routing, other than the aspect that we're looking at a delivery group for getting the message to the best possible mailbox server that we can for delivery. Failback is relatively the same as well in terms of this. We still want to fail back along the least cost route. Now, there are some nuances here. If you have a DAG, and that DAG is stretched across multiple Active Directory sites, then we're going to choose, we're going to target the mailbox servers in one of those Active Directory sites generally, the Active Directory site that is closest on the least cost route as opposed to the other one. Once we get a message to the final destination delivery group, we will not back off any further because we're already at the closest available hop that we can get that message to. Otherwise, in the event that we can't get that message to the final destination delivery group, we will back off accordingly along the least cost route up to back and keeping it at the source if there is no transport service within the target Active Directory sites along that least cost route. Selection is going to be scoped within this delivery group is going to be scoped based on recipient type. Again, this comes back to the mailbox, the version of the mailbox, whether it's or a mail-enabled object, distribution group, mail-enabled contact, and the like. Client access servers, the front-end transport service, also takes into account delivery groups when routing. But it does not do any advanced inspection upon those recipients, as we'll talk about in some of the routing scenarios. So I have 8 specific routing scenarios to kind of cover today. Multi-role servers, dedicated servers, legacy, client submission, and then we'll talk about transport high availability. So the first one is a multi-role server. A single server that has both client access server role and the mailbox server role. I have a message coming in. The front end is going to receive that message on TCP 25. The front end transport service, there we go. The front end transport service will do a discovery, determine where that mailbox is located. In this simplistic example, the mailbox is going to be located on the local box because it's a single server. We'll deliver that to the transport service via TCP 2525 since we're a multi-role box. And then we will deliver that message via the transport delivery service on TCP 475. That message will then get delivered, be converted from MIME to MAPI, and delivered to the store. Make sense? Go more complex as it goes on. Things I want to call out within this protocol flow. I have the internet client submitting this message. Notice that the communication starts to the front-end transport service. So I do my hello, I get my acknowledgement. I do my mail from, I get my acknowledgement. I do my receipt to, I get my acknowledgement. I then start the submission of the data. Once I start the submission of the data in this unauthenticated scenario, that is when the front-end transport service will establish an SMTP session with the transport service. That session will be encrypted via TLS. It will initiate the hello, and we have a new proprietary verb that we leverage, xproxyFrom. XproxyFrom contains all the details about that client that is submitting that mail, the client IP, the client name, etc. All the information we need so when we do message tracking and the like, we know exactly where this message actually originated from. Because the front-end transport service is just you can think of it as a dumb proxy in some regards. It's an intelligent proxy, but it's not one that's actually relaying the message entirely because there's no queue. It's just passing this information on. It becomes a blind proxy at this point. It then initiates the mail from, we get the acknowledgement, the receipt, the acknowledgement, the data, the acknowledgement. Transport service is then going to deliver this message to the mailbox transport service within that delivery group. The mailbox transport service is always going to be that protocol instance that is local to the active database copy. So this could be a different server. In our case, from the previous demo, it was a single server. It also uses additional parameters. The X-session params, which, as its name implies, includes some parameters about the session that it's establishing, and the X message context, the specific context associated with the message, some message properties that have to be associated, that have to be used for delivery. And then it acknowledges that. Once we're finished, once the transport service has received all the data, it will issue the acknowledgement back to the front-end transport service that we have completed this, which is blindly passed back on to the internet-based client. So we get the 250 OK back to the client. He knows at that point the session's done and we're over at that point. As you can imagine, the receive headers might look a little different now in 2013. So I'll start from the bottom. Typically, you see you're from, who's it coming from, you get a message ID, and you have a subject. Then you'll have your first received from header. In our case, we will see that it's received from the internet by a particular Exchange server. You can excuse the long, crazy name of our test topology. And you'll see what I've highlighted there, via front-end transport. This is one of the first things that we added in Exchange 2013 in the headers, is to give you a nomenclature around which particular transport component is processing this message. So there's two of them specifically. The first one is via front-end transport. We will then see the message proxied from the front-end transport to the transport service. Looks very similar to what we used to see all the time. And you can see that it was with Microsoft SMTP server. That's our transport service. And it gives you the version number. In this case, this was a build prior to CU1's release, so 620.3 instead of 620.29. And then we will see another header in this case, via the mailbox transport header. Now, because this was all in one, you see the same server name repeated throughout, EXHV-1889, because it was all a single server scenario. But you will see this broken out, obviously, if you have dedicated server roles or if it's moving across different server roles as message delivery occurs. But that's how you can distinguish which particular component is actually processing the message on the message headers. But at minimum, you'll have three. So, two multi-role boxes. So an actual DAG in this case. So we have a message coming in from the internet. Which front-end transport service will we use? Well, we're going to use whichever one that the load balancer assigns to route that particular connection to. So the load balancer makes that determination of which server, server 1 or server 2, is going to receive that connection on TCP 25. In this case, it chose server 2. Server 2 receives that message. Now, this message is destined for two recipients. And it so happens each one of those recipients' active database copy is on different servers at this point. So we have a recipient on server 1 and a recipient on server 2. Now, the important thing here is that because we have multiple recipients, the mailbox transport service, because it doesn't do any advanced inspection of this message, doesn't do any categorization, really doesn't look too much around the recipient list. It looks to see primarily a few things. Is the recipient a mailbox, or is the recipient a mail-enabled object? That's the first thing it looks for. It also looks for the version of that mailbox, because we have to make different decisions, as we'll talk about in a later scenario, based on the version of that particular mailbox. It looks to see also how many recipients we have. If we have more than one recipient, then we are going to evaluate 20 of those recipients, and we're going to choose to route that message to a transport service, the best transport service we can, which is generally going to be the transport service, a transport service that is local, meaning in the same Active Directory site as the client access server that's currently processing this message. If it's a distribution group, so a mail-enabled object, a mail-enabled contact, or a distribution group, we don't do any expansion of the membership, so we simply route that to a transport service. Again, giving proximity to a transport service that is within the same Active Directory site as the client access server role that's processing this particular message. So front-end transport service, we'll see that we have two recipients. In our case, these two recipients are located within the same DAG. So our delivery group is a routable DAG in this case, and the delivery group happens to be the final delivery group, this particular DAG. So we just hand that off to a transport service within that delivery group. Now in this case, for the purposes of the demo, I showed that we handed this message off to server 1. We could have equally have chosen server 2 for handing off this particular message. It doesn't matter. We want to get it to a transport service within the delivery group. So it could have been any of the servers within the DAG, within the local Active Directory site that we would have given preference to. Transport service at this point is then going to categorize this message, determine we have two recipients, determine that those recipients are located in different Active Directory databases, and those, are located in different active databases, and that those active databases are mounted on two different servers. We'll bifurcate that into two copies, submit that to the mailbox transport service that is local to the active database copy for message delivery. Now, what would happen if at the point that we got here and we created that, we had a failure on server 2, and the database on server 2 now became mounted on server 1? Well, probably because we were already in this process, the message would still get delivered to the mailbox transport service on server 2. But because the database is no longer active on server 2, the mailbox transport service will ultimately reject the connection, forcing the transport service to do a new lookup to see where that database is now mounted and find that it's located on server 1, and the transport service would then deliver that message to the local transport service, mailbox transport service on server 1. So mailbox transport will only ever deliver a message to the store that is local to it. If that store or database fails, it will reject the connection. And it's a specific error code that is used that I don't remember off the top of my head. And then mailbox transport will do the content conversion, deliver via local RPC to the database, and that user can now consume that message they just received. Make sense? Am I putting you all to sleep? Okay. I know it's after lunch. I'm tired. Was there a question? So the question is, what happened to the edge transport server role, and what can I do? So currently, there is no edge transport server for Exchange 2013. We are constantly evaluating feedback and adjusting our plans as need be. So we will take your feedback under advisement. I did my marketing correct answer. Is anyone from marketing here? Good. So let me finish this one first. So today, if you still want to use Edge Transport, then yes, you would still want to leverage an Exchange 2007 Edge Transport server or an Exchange 2010 Edge Transport server, whichever one you have deployed. You can create an Edge subscription with the mailbox server role of Exchange 2013 so that it can participate in that in Edge Transport delivery and submission, and can do the Edge Sync protocol. Yes?
Can I combine DAG members from 13 to the 10?
No.
Different DAG.
Yes.
But I can coexist in the same environment.
Yes. DAGs, yes. The Exchange 2010, Exchange 2007, and Exchange 2013 can all coexist within a single Active Directory site or multiple Active Directory sites, but there is a distinct version boundary. Windows failover cluster has to, the OS of Windows failover cluster has to be the same operating system, and we require the same version of Exchange within a DAG. Is there a question in the back? Yes?
In the front-end transport, if you don't have queue, what happens if you have failures from the outside to the inside? You didn't give any knowledge back to the outside. So what happened in this case?
So in the event that both these transport services are non-functional, the front-end transport service will reject the connection. So, because if you go back to this slide. You can see when we accept the connection, a front-end transport, and we go all the way up to the data verb. Once we get to the data verb, we attempt to establish a TLS session to a transport service. If we can't accept a TLS session to any transport service within that delivery group, we'll reject the connection at that point. Yes. To put the onus on the submitting client that they have to deal with it, since they are the last successful hop.
So is it, sorry, a question then. Is it data transferred from internet to the actual transport, or is it through the front-end transport?
It is through the front-end transport. The internet client never connects directly to the transport service. It's a blind proxy at that point, which is why you see it just passed.
Like an MSG through the hard drive, or how is it?
It's just, it's, the best word I can use, streamed. There we go. Okay. Yes, one last question.
Was the data written to disk during the proxy process, or is it just in RAM?
It's just in RAM. So, taking the second example and now reversing it. Instead of having mail coming in, let's have mail leaving the mailbox server role. So again, I have a message here from this recipient on server 1, and I'm going to want to submit this message, and I believe I have 3 recipients. I have another recipient on server 1, a recipient on server 2, and a recipient on the internet. Message going on is going to be, we're going to submit this message to the MS Exchange submission service, the mailbox transport component. Now, there's my 3 recipients. We will submit this message to the mailbox transport component. Now, again, because of every server's an island, we're going to submit this message to the local MS Exchange submission process, the local mailbox transport component. Mailbox transport component at that point can choose any transport service within the DAG for submitting that message for its destination. So in this case, we choose server 2. Once the message gets into the transport queue, we'll categorize that. We're going to bifurcate. We'll create 3 copies because we have 3 unique recipients that exist in 3 different places. We have a recipient on server 2, we have a recipient on server 1, and we have a recipient in the internet. The transport service will then deliver those messages accordingly. So since we are within the final delivery group, the transport service is simply going to submit those messages to the mailbox transport process that is local to the active database copy for those particular recipients. So we submit it to the mailbox transport service on server 1 and server 2. In the case of the internet recipient, again, it's going to go back to how we have the send connector configured. I'm making an assumption in the slide that we have pre-configured our send connector by executing it, set send connector front-end proxy enabled $true, and we have the ability to proxy those messages through the client access server roles front-end transport service. So we will choose a front-end transport service within that Active Directory site, and these messages will then get delivered to their final recipients. Protocol flow here is very similar to what I showed in the first example, but is just the reverse. We start at the mailbox transport component. We establish a TLS session for SMTP to the transport service. We do our hello, our mail from, our receipt to. We send the data. The transport service, once that message is queued, will then establish a TLS session with a front-end transport service. Use the xproxy2 to provide all that information about that submitting client, the mailbox transport component in that particular case, and stream all that information over. And then that front-end transport is processing that message to the final destination, the internet-based client. So now, let's look at a more convoluted example. And by convoluted, I mean I made it really convoluted. I decided to take a DAG, and I stretched it not across 2 sites, but 4 sites. So we have a DAG member in each of the 4 sites. We have CAS in each of the 4 sites. Now, and not only that, but we decided to share the namespace across all 4 sites. So mail.contoso.com can resolve to any one of those CAS and any one of those Active Directory sites. Pretty wicked, huh? I have an internet-based client. He wants to deliver a message to 4 recipients. And as you can imagine, each one of those recipients exists in each site on a DAG member. So, again, because of load balancing, we're going to choose one of these front-end transport servers. In this case, we chose the 3rd guy, AD Site 3. Front-end transport service receives that message. It's going to see that we have multiple recipients. Those recipients are mailboxes. It's going to say, I need to deliver this to the final I need to deliver this to a delivery group. Let's see if I can deliver it to the routable DAG. In this case, I can. I'm going to choose to deliver this message to the transport service that is local to me. So it goes to the transport service within Site 3. The transport service is then going to bifurcate that message, create 4 nice little copies, and then we'll deliver that to the mailbox transport component within this DAG, because all the recipients already are within this DAG, so we're in our final delivery group. So each message will go to the corresponding mailbox transport service on the mailbox server hosting the active database for each user, and then we get that message delivered to the user's inbox. Pretty nifty, huh? So let's add a 5th scenario. What happens if this internet-based message was actually destined to 5 recipients, and the 5th recipient happens to be a 2010 mailbox? So the first half of the process is all the same. Message goes to a CAS. CAS is going to send that to the transport service that is local within its Active Directory site. The transport service is then going to bifurcate that message, and instead of creating 4 copies, it's now going to create 5 copies. Now, the first 4 copies, the ones on the top, they're already in the final delivery group, because their final delivery group is this particular routable DAG, so they get delivered to the mailbox transport service on their respective servers for delivery. The 5th message is not in its final delivery group. Its final delivery group is a mailbox server delivery group, and that mailbox server delivery group happens to be the E2010 mailbox server that's sitting out in AD Site 4. Transport doesn't deliver directly to mailbox servers. Transport has to do what we've always done in 2010 and 2007. We have to deliver to the respective hub transport server version. So we will route that message to the hub transport service within that Active Directory site, that the hub transport server can get it to its final delivery group, which happens to be the 2010 mailbox server. Hub transport will then deliver that message, and the message is delivered to the 2010 user and all the 2013 users. Does that make sense? So let's talk about client submissions. So with client submissions, I'm being very specific here. All the previous examples where messages were coming in were all unauthenticated submissions, right? They're all from an internet-based client. Whereas in this scenario, we're talking about an authenticated user. So I have, I don't know, let's call her Mary. I have Mary, who happens to be jet-setting around the world and happens to be in Site 2 for her environment. Her mailbox is actually located in the DAG that's located in Site 1. We are sharing the namespace across these 2 sites. So mail.contoso.com or mail.fabricam.com can resolve to either one of the CAS in Site 1 or Site 2. Mary's going to pop open her IMAP client. It's going to authenticate. It's going to do a DNS lookup from mail.fabricam.com. It's going to get back a CAS within Site 2. She's going to authenticate against that CAS in Site 2 and submit her message. Now, upon her authenticating, we're actually the front-end transport service is actually doing a lookup of where Mary's mailbox is. It finds that Mary's mailbox is in the DAG in Site 1. So we're actually going to submit this message to the transport service, to a transport server, to a transport service on a mailbox server that is located in the DAG in which her mailbox resides. The transport service in that site, in Site 1, in this case I chose that it was going to Mary's actual mailbox server, but it doesn't have to. It could have gone to M7 in Site 1, for example. The transport service will then evaluate who that recipient is and deliver that message accordingly. That could be another DAG. It could be delivering that message to a DAG member in Site 2 at that point. It's all, again, or in this case, it's going out to the internet. But it's all, the key thing about an authenticated submission is that the front-end transport service, again, doesn't have any super intelligence around recipients. So it's simply, in this case, because it's authenticated, it will route the message to a transport service within the DAG or to the mailbox server of the sender. And then that service will then route that message accordingly to the target destination, whether that be another delivery group, like another DAG, or it would be a internet client and thus go out through the front-end transport service again. So the protocol flow is a little different here because it's authenticated. You'll see that we do the eHello, we get back our acknowledgement, we then establish a TLS session, and we authenticate. At the point that we authenticate to the front-end transport service, the front-end transport service will then start its session to the transport service in the delivery group that is based on the sender. So in this case, then establishes that session to Mary's server. We do our X proxy and pass all the information that's relevant about Mary's client. And then we become, the front-end transport service at this point becomes a blind proxy. Whatever commands that are issued by the transport service are passed directly to the client. Whatever commands that the client issues are passed directly to the transport service via the front-end transport server role. Front-end transport role doesn't do anything special at this point. It just passes the verbs and the data associated with those verbs directly to the transport service. Same scenario as the previous one, except I have my senders now a legacy mailbox. So Mary's mailbox is on Exchange 2010. But we've already moved we've already introduced Exchange 2013 in the environment. We've already moved our SMTP namespace to the client access server role. So when Mary authenticates, she's going to be authenticating against a front-end transport server role. The front-end transport server role is going to do that lookup on Mary. See that Mary's mailbox version is 2010. It will then route that message to a transport service that is local to itself, because the front-end transport service does not communicate with legacy transport servers whatsoever. It only communicates with the 2013 transport service version boundaries. So we prefer the local Active Directory site in this case because we can't do any specific resolution. So the transport service on the DAG1 member in Site 2 receives that message, categorizes that message, and says, okay, I can then deliver that message. In this case, our target recipient is a user in DAG2. We're going to choose a transport service in DAG2. In this case, our preference along the least cost route is going to be the local transport services within AD Site 2 because AD Site 1 is another hop, right? So we'll get it to the final delivery group, which happens to be a transport service in DAG2, one of those 4 services in Site 2, and then the transport service will hand that off to the mailbox transport component on that server in DAG1, and that will get delivered to the user. Make sense? So let's switch gears and talk about high availability. In Exchange 2010, we introduced this concept of shadow redundancy. Shadow redundancy basically said that we expect that the previous transport server will redundantly persist a copy of that until the next hop in the transport delivery pipeline has received the message. So we were always requiring the previous hop to create a shadow copy. In Exchange 2013, we've inverted that. We no longer want the previous hop to do it. It's now the first hop within the final delivery group. The first hop is responsible for creating the shadow copy. This is what we refer to as guaranteed redundancy. And these shadow copies are kept similar to the way we keep the active copy. They're kept in a shadow queue within the mail.q file, very similar to how we did it in the past. So nothing there really changes, other than we inverted the way we do it. We no longer wait for the previous hop to keep it. We now enforce it at the first hop. The other interesting dynamic that we've done in Exchange 2013 is that we've made the DAG the transport boundary for high availability. So I'm sure all of you have dealt with transport dumpster in the past, right? Yes? No? Yes? Okay. Transport dumpster, great idea, but it had one nagging problem. It was a single point of failure. If that transport queue was lost, that mail.q file was lost, all the data in that transport dumpster was lost with it, which means in the event that you needed to do a lossy failover and you needed to recover, you didn't have that data. Which, also when you're thinking about site resilience scenarios, meant that you didn't have transport resilience. Because if you're operating out of site 1, and all your transport servers are in site 1 delivering mail to the mailbox databases in site 1, your transport dumpster is in site 1, effectively. Site 1 goes down hard, you have no means to get to that data, and you have to activate in site 2. You're going to mount those databases in site 2. They're going to be slightly behind, most likely. Maybe it could be seconds worth, or it could be minutes or hours worth, depending on your network capabilities. You're going to mount those databases, and you're not going to be able to recover any of that data in the transport dumpster in Site 1 until such time as Site 1 comes back up. And if it's within our window, we will redeliver those messages. But if Site 1 is a smoking hole, you've lost that data for good, right? So there's a problem there. So we addressed that in Exchange 2013. The DAG is the boundary for high availability. So it only makes sense that the DAG should be the boundary for transport. So now, when we get a message into that delivery group, we're going to redundantly persist a copy of that message within the DAG. Not only that, but we actually give preference to storing that shadow copy in the remote Active Directory site when you have a DAG stretched, which means you now have site resilience for your transport queue in terms of recovery. Is that not cool? And then to ensure that we make it operationally easy, the recovery is simplified as well. Anytime there's a lossy failure, we'll automatically resubmit requests to get that message redelivered from either the primary copy or the shadow copy. This works when you do a typical failover and a database is mounted automatically by Active Manager in the replication service. This occurs if you invoke the move active mailbox database and you specify the accept data loss parameter. You can even invoke it manually. You can run the add new resubmit request or something like that. Add new resubmit request. That's the commandlet. New resubmit request. And you can invoke redelivery manually if need be. So there's multiple ways to do it that typically don't involve any manual requirement. Even lag copies, if you activate a lag copy, will submit a redelivery request or a resubmission request from our high availability queue here. And that's what in this high availability queue is what we refer to as safety net in Exchange 2013. We no longer refer to it as transport dumpster. Safety net was something that we actually introduced in Office 365 back in Exchange 2010 that we really didn't talk about until Exchange 2013 shipped. But it is similar to transport dumpster. However, it is different. Because like I said, transport dumpster had a single point of failure. The other key difference between safety net and transport dumpster is that in Exchange 2010, transport dumpster was the messages were persisted in the dumpster based on a replication feedback loop. If the messages had been inspected on all copies, we could remove that message from the transport dumpster because we were already guaranteed the logs pertaining to that message had already replicated across all copies within your high availability framework. We've removed that component of safety net. Safety net is entirely time-based. We keep the messages redundantly persisted for a period of time. The out-of-box configuration is 2 days, which also ties in with your default, the default message expiration queue. As I mentioned with safety net, we also attempt to redundantly persist those in another Active Directory site in the event that you have a stretched DAG. Now, the key thing there is if you're one of those customers that likes to stretch your Active Directory site across data centers, you won't be able to guarantee you get redundant persistence across the data centers because we don't know what data center we're operating in. We only know the Active Directory site topology. So we can only guarantee it's redundantly persisted in a remote site if you have your Active Directory sites split across the environment. If you stretch your Active Directory site, we can't guarantee it. The way it works is the default configuration prefers the remote site when it creates the redundant copy, the shadow copy. We will attempt to create it up to 4 times. So if we attempt to establish on server 1 in AD site 2 and that fails, we'll attempt server 2, we'll attempt server 3, we'll attempt server 4. If after the 4th attempt we still can't create a redundant persistent copy, we will attempt to create the copy in the local Active Directory site. If we fail creating the local copy 2 times, we will then end up rejecting the connection altogether, and we won't allow message delivery at all into that DAG because we can't create our persisted copy. That's a specific error code response 450.4.5.1 in the event that you are troubleshooting things and you see that error message come up in your 2013 environment. We do recommend that with safety net, Scott touched on this earlier in the high availability talk, that if you are deploying lag copies and you expect that you will at some point activate the lag copy for recovery, whatever your replay lag time is, your safety net time, hold time, the property is safety net hold time. Safety net hold time either needs to match your replay lag time or exceed your replay lag time. Because otherwise you won't have the data in safety net, especially if you do what our preferred approach for how you activate the lag copy, which is you don't use the log files, you just mount the database. And whatever that lag time is on that database, that's how far back that database is at time. So if you have a 7-day lag and you mount the database, you're 7 days behind in mail. That's where safety net comes in. Safety net will redeliver all 7 days of the past mail and get that database back to being current to a degree, since safety net doesn't keep things like message read or unread or local appointments or things like that. But that's why you need to increase the safety net hold time. So let's look at this in particular. Instead of animating this slide, I decided to take the actual example that we use in TechNet and I just decided to walk through it so it would make sense. So we have 2 servers within this DAG. Remember that DAG is our transport high availability boundary. So step 1 is that MBX01 is going to receive that message from a server outside of the high availability boundary. So this could be another mailbox transport. This could be another transport service on a mailbox server in another DAG. It could be a front-end transport service. It could be a third-party SMTP stack that you're having delivered directly into the transport service. Step 2 is that before we ever acknowledge the receipt, so before we ever issue the 250 OK after the data verb has passed, we actually will delay the 250 OK at that point. And we delay it so that we can actually create our copy. Because remember, if we couldn't create our copy, then there was no way we could issue the rejection, that 450.451 response. So we have to delay the acknowledgement of the data verb so that we can try and create our persistent copy. So we'll create it. In this example, you can see that we will create it on another server. We won't create it on the local server because then we would have a single point of failure. We'd have both our primary and our secondary copy on the same server, and that's a bad design. So we always prefer another server. Since I don't show an Active Directory site topology, but this could be, mailbox 1 and mailbox 3 could be in different Active Directory sites. We'll create that. Within the mail.queue, we actually have a specific queue called the shadow queue. That's where we place that copy, the shadow queue. The message is retained in the shadow queue for the entire lifetime that the message is in transit. Once the message is delivered, we'll then move that. But I'm getting ahead of myself. That's step 5. So step 3, there's multiple steps to step 3. The first one is that the transport service on mailbox 1 is going to process that message, and it's going to attempt delivery via the mailbox transport component. Now, that mailbox transport component could be the local transport component. It could be a remote mailbox transport component on another server in the DAG. Really depends on what the recipient is in this case and where the active database copy for this particular recipient is located. The mailbox transport is then going, in turn, deliver that message to the mailbox database. At that point, the transport service on mailbox 1 is going to queue a discard status notification for mailbox 3. This tells mailbox 3 that he can now move that message out of the shadow queue and move that message into the safety net queue. So we use the shadow copy. The shadow copy ultimately becomes our redundantly persisted copy for safety net. So we don't create multiple copies. We just create 2 copies. We have the primary copy, and we have our secondary copy, or the shadow copy. The shadow copy is always the copy that will be redundantly persisted for a period of time. Mailbox 3 is going to poll for delivery status and see that we no longer detect that discard status notification, and it will ultimately move its copy from its shadow queue to the shadow safety net queue. So, in review, we have 3 key transport components now in Exchange 2013. We have the front-end transport component on the client access server role, which is a stateless component that facilitates and provides us a unified namespace and network load balancing transport infrastructure for messages either entering into the Exchange organization or messages leaving the Exchange organizational boundary. And then we have the transport service and the mailbox transport service components that reside on the mailbox server role. The transport service is our stateful engine that provides our queuing and our routing, inspection, and enforcement capability. And then we have the mailbox transport service, which, as I mentioned, you can think of it as conjoined with the store, because it always ensures our every server is an island principle by being the component that delivers the message to the active database copy on the same server. And then we ensure we've optimized our high availability and resiliency framework for transport by introducing our guaranteed redundancy functionality and our safety net features to persist messages throughout the lifetime that we need them for recovery. Any questions? Yes. Since we actually have some time, why don't you use the mics? That way it'll get recorded. Thank you. I had to save my voice a little bit from repeating.
On the safety net, on the previous slide, when you show like server 1, server 3, whatever the numbers are,
Yep.
what's the recommendation network latency between, especially when you do a stretch DAG? What's the network latency recommendation on here?
Well, our guidance is
30 milliseconds still?
500 milliseconds.
What was the
But
number?
I would never deploy a DAG with 500 millisecond latency. The latency is ultimately going to come down to what you want in terms of database health. The more latency you have, the longer it's going to take to replicate, which means the more behind your database copies are going to be. So there's no one magic answer because it's greatly dependent upon your environment.
On the safety net, I mean, you might have to start creating a queuing if you're waiting to acknowledge back, if you have a long latency, right?
Well, if we can't establish a connection, we will attempt another server, and finally we'll fall back to doing a local copy. And all those parameters are configurable on the transport config object.
So you could,
as well.
these adjustable. You could change
Yes.
like how many tries and stuff.
Yes, you can even change it. Like I said, the default behavior is to reject the connection. You can actually change that so you still allow the connection. So you're basically saying at that point, I'm willing to give up redundancy to ensure message delivery.
Okay. Thank you.
Yes.
Is this one on?
Is it not on?
I think it's on now.
Yeah.
So right now we've got a 3 data center model, 2010, DAG stretched across all 3.
Okay.
2 of the sites, say 1 and 3, are internet facing, so messages can come into either one, and then they just talk hub transport to hub transport. Those mailbox copies are essentially inactive, the ones in sites 2 and 3. Everybody's active in 1.
Okay.
All right. If I emulate that in 2013, I'm not going to have inactive mailbox copies if I have an internet-facing site, correct? Because the CAS will hand it to the mailbox, and the mailbox will talk to the mailbox in site 3 will go to site 1.
Yes.
Okay, because we sort of counted on that model as guaranteed maintenance windows. We knew that the mailbox servers were never doing anything except replicating logs.
Yeah.
But in 2013, that's not a possibility.
Well, CAS will, if the only CAS that will actually be receiving mail from front-end transport will be the ones in the internet-facing site that
Right,
you
one and-
have
one and three,
associated to the
yeah.
load balance pool. And at that point, they're going to deliver to, if it's multiple recipients, they're going to basically they'll choose a DAG, they'll choose a delivery group, which will most likely be, they'll prefer
The whole DAG, right?
they'll prefer a routable DAG. If you have a mixed, like in one of the examples, I didn't show the reverse, but if you had a mixed set of recipients, 2013 recipients and 2010 recipients, all in one message, we're going to prefer routing. Well, we're always going to route to a 2013
Right.
server for delivery. But we'll choose one of the DAGs, giving preference to a DAG member that is local to the CAS instance.
Right, okay. So it'll always deliver to a mailbox server in 3, even if the active database is in 1. Because they're on the same DAG, it's the same boundary.
Yes, if CAS is in 3 and that's where
Yes.
your delivery is, then yes, it will go local.
Okay, I just wanted
And
to
then
get it clear in my
yeah.
head that I'll have to count them all as active, so.
Yes.
Okay, thanks.
Yeah, just wondering about the storage implications of the shadow safety net, because you're recommending that the transport services are all staying on the system drive of your thing. Now, if you set, in your example, you said 7 days in order to potentially redeliver that chunk of mail.
Yep.
Now, in my organisation, 7 days of mail would definitely be more than any possible C drive. So, can you move the safety net, and can you limit the amount of space that it takes?
Well, yes. Yes and no. So the default for safety net is 2 days.
Yep.
And you can set on the transport config or transport server. One of the two does safety net hold time. Might be config. Yes, it's config because message queue expiration is transport server. You can set the safety net hold time to be a value that you want, but like I said, if you're deploying lag copies, it needs to match the replay lag time. And you'll get a bunch of warnings when you set it. It says, hey, the replay lag time's X, you need to be doing this.
But if I wanted to set a longer one that wouldn't fit on my C drive, can I move the safety net somewhere
the
else?
mail.q can be, like you did in 2010 and 2007, you can move the mail.q file and its corresponding log files using the web config file, the config file. Our sizing guidance and the calculator both take into account safety net and message queue expiration times and the message profile to build how much space we suspect will be needed, and there's some fluff in there.
Cool. That's great. That's all I need. Thank you.
Yeah, and we even say you can deploy your system drives on 7,200 RPM disks. So you can get 4 terabyte disks for your system drive and have a large transport queue as a result. Yes. Whichever one wants to go.
I have 3 questions, so I'll wait till
Okay.
everyone else is gone.
All right. You're up.
In a scenario where you have a coexistence between 2013 and 2010, is it not necessary to have a 2010 CAS to receive proxy requests from the 2013 CAS, since the 2010 is the RPC endpoint?
Yes. So, yes, you're not deprecating CAS. You're not deprecating 2010 CAS, 2010 Hub Transport, 2010 Unified Messaging until your last mailbox server is removed. Your last 2010 mailbox server. So a client connection, a 2010, a user request that comes in through a 2013 CAS, and the version of the mailbox is 2010, we will proxy that request to a 2010 CAS, typically in the Active Directory site where the mailbox is located.
Okay, I only asked, I thought I saw in your diagram where the 2013 CAS proxy to the transport for.
Well, that's transport. I gotta remember where that slide is. This one?
Well, it wasn't the one with the multi-site DAG.
Oh, okay. Yeah, so
Yes,
this
this
one,
one.
this is all transport. So front-end transport service is going to deliver the message to a transport service within 2013. The 2013 transport service will then route that message to the final delivery group, which happens to be a 2010 mailbox server. So that has to be delivered to a 2010 hub transport
So
service.
there's no need
Front-end
for
front-end transport service will never talk to a 2007 hub transport or a 2010 hub transport. It only can talk to 2013 transport service, or technically later, 2013 or higher.
If you have an inbound message that's to multiple people on the same server, at which point does it get split up?
Well, if the message is to multiple people, then the transport service won't bifurcate that into multiple copies. It'll just deliver, if they're all in the same store. If they're on different stores or different databases, then a message will be created for each database.
Well, in this case, if you have a message that comes in and it needs to transition a site boundary, is it going to send that whole message over as one with all of its recipients, or is it going to split it up and then send it over the site boundary?
It will. We prefer to reduce the number of copies. So our goal is to not split it up, if at all possible.
Okay.
Other actions could force that, like journaling.
Okay.
I have a question in regards to outgoing mail.
Yes.
I was just curious how, when a message gets delivered to mailbox transport, how it decides which transport service to use for outgoing
When a
mail.
message gets delivered to mailbox transport,
Yeah, for mailbox transport, how,
Wants to do a
how it
delivery?
decides which transport service to use.
mailbox transport will always deliver to the local transport service.
Even for outgoing mail?
I'm going to correct myself. Mailbox transport can deliver to any transport service within the DAG.
Okay. But how does it decide which one to use?
It's entirely random.
No. Okay, thanks.
Ross, excuse me, Ross. One of my questions is actually in relation to that. So because the mailbox transport service can randomly choose any transport service in the DAG or in the AD site, you potentially can generate additional traffic, because if you choose a transport site, a service that's on a server that is not hosting the active copy of the mailbox, but it's actually hosted on the server that generated the message, you potentially sent the message across your network twice.
Yes.
And you didn't need to.
There is the potential for that.
So is there any way to prevent that?
No.
Okay. All right, thanks.
Yes.
Could you Could you give a little detail on how the messages are delivered from the active queue to the shadow queue? Like, what's the delivery method?
I'm sorry, I couldn't hear you.
Could you, the delivery method between the active queue and the shadow queue, how does it actually deliver that, the message? Is it split into like logs, or is it as a whole message, or?
It's the whole message stored in the queue,
So it's
and it's
just
just
a copy?
moved. So when the active copy is the one that's actually going to be delivered to mailbox transport for delivery to the store. And then the shadow queue is just a secondary copy of the message.
So it just copies the whole message, and that's
It's a copy of the whole message.
So if it's a large message, it
Yes.
could be a rather long.
Yeah.
Okay.
So if it's a 20 meg message, you have 40 megs worth of data stored in the environment, right? Because you have a copy on server 1 with 20 megs, and you have a copy on